My name is Michael Szymkowski, and today I want to talk to you about my research in the field of reconfigurable and parallel computing with FPGAs. So I'm going to talk about the idea of an FPGA-based parallel computer. FPGAs have been around since about the 1980s. They've been used for the testing and debugging of digital circuits before their fabrication. But now I'm going to talk about their place in the field of high-performance reconfigurable computing. So this is going to be a very interesting discussion. We're going to talk about some of the advantages that FPGAs have that has given them a foothold in this field, as well as some of the drawbacks and improvements that are going to have to be made. So the first thing I want to clarify real quick is the true meaning of parallelism. There's many words that people throw around involving parallelism. I want to talk about multi-programming, synonymous with multitasking, and multi-threading. So what we really want to do is we want to get the true meaning of parallelism so we can proceed forward with our discussion. Okay. So on these diagrams, first you're going to see multi-programming, which is synonymous with multitasking. So you have one CPU and you have multiple processes that share that CPU. A CPU can only run one task at a time, so each of these processes only can be served one at a time. So they may be time sharing the CPU, but they're not actually running concurrently. There is an illusion of it being so, but it is not actually concurrent. So multi-threading is true parallelism, because you have multiple CPUs, multiple processors in a system, as well as these different tasks, I'll call them tasks for the moment, running concurrently on each CPU. So consider a high-performance computing application, a very data-intensive process. Why not split it into sub-processes called threads, hopefully that can run concurrently, and have them run on each different processor? That is true parallelism. Alright, so now moving on to reconfigurable computing. So reconfigurable computing gets the best of both worlds of two methods for doing computation. The first is application-specific integrated circuits, which are fabricated circuits meant to do one job. They're optimized for what they do. However, they can't be changed once they're fabricated. Processors, on the other hand, like a microprocessor or what you have in your computer, interpret instructions, like the fetch, decode, execute cycle. So they have lots of flexibility, but they're not as fast as ASICs because they're not optimized for the tasks that, for any particular task. They do lots of different tasks. So let's talk about the construction of FPGAs really quickly. So FPGAs are made of logical blocks that I want to just quickly go through. So these logical blocks are made of three things: lookup tables. So lookup tables, essentially just a digital implementation of a truth table, which, as you know, digital circuits should be able to be represented by a simple truth table. Very useful. D flip-flops. These are very important for implementing sequential circuits as well as pipelining, which we'll talk more about. And then full adders for arithmetic operations. All right, so now we're going to talk about the size of lookup tables really briefly. So lookup table size has been researched. Obviously there's the idea of too big lookup tables waste space, too small. There's more overhead in communication because you need to communicate between lookup tables. And they've settled on lookup tables of size 4 in general in industry. So we'll talk more about that a little later. So I want to introduce the reconfigurable computing concept. So the process of reconfiguring hardware during execution is known as runtime reconfiguration. There's obviously a trade-off here. Reconfiguring hardware, which is really corresponds to synthesis of an FPGA, takes time. There's overhead to it. However, when you resynthesize something correctly to optimize it for the task it's about to perform, you will have a drastic speed up depending on how well it's optimized or how optimizable it is. So there is a trade-off, but if the overhead exceeds your benefit, there's no sense in doing the reconfiguration. All right, so our solution to the problem of overhead may be you could just partially reconfigure the hardware, just the part that needs to be reconfigured. Lower overhead. So really quickly, an advantage of FPGAs, which we'll talk about more, is that they can implement any size data widths. So standard processors implement only fixed data widths, which means you could waste a lot of space in computation when it's not necessary. However, FPGAs can be optimized to the exact data width you need. So FPGAs for reconfigurable computing have been driven by, obviously, their development and their availability. A lot of FPGAs are considered cheap prototyping tools meant to prototype circuits before they're fabricated. However, we need a really quick synthesis time for reconfigurable applications, so there's obviously a trade-off. Alright, so now, there's 5 main architectures for reconfigurable computing. I want to go through them briefly here because I think they're important to understand. First, we can have reconfigurable hardware that only is meant to provide extra functionality to the processor. It's called a functional unit, and it's embedded in the processor itself. So there's really no parallelism here at all. Simply, it is used to aid the processor in the execution of special instructions, just like we talked about, which it may not be optimized for. Second, the reconfigurable hardware can be used as a coprocessor. So a few things to note about the coprocessor. A direct data link between the coprocessor and the CPU, sharing of the cache, and sharing of the I/O interface. Very tightly coupled. This does not have a large degree of parallelism because they're very tightly intertwined. The next one is an additional processor in a multiprocessor system. So as you can see, we're getting further and further away from the first one, which is the fabric embedded in the CPU. We're getting towards a more looser structure. So here, it shares I/O, but really nothing else. So this is the reconfigurable processor. Fourth, it can act as a external standalone unit. So you can see it really doesn't have any connection at all, other than the fact that the CPU can communicate with it through its I/O interface, which is very slow. So for this, you don't want to have an application where the CPU needs to be very involved with the processor. The processor needs to be able to execute by itself for quite a bit of time. An example of a standalone unit would be, for instance, if you have an image in MATLAB, you could convert it to hex, you could dump it onto an FPGA. FPGA could do some simple image processing like thresholding, brightening, etc., and then give it back to you. That would be an example of like external processing. And finally, the last one is programmable fabric, which is the exact opposite of the first one. The CPU is now embedded in the programmable fabric. They're all summarized here. If you get nothing else from this, please note that as you move from the fabric to the coprocessor to the attached processing unit to the standalone unit, you're getting more and more loosely coupled. So the parallelism degree increases as you move towards this standalone unit. However, the overhead and communication also increases. So it's all about your application. Now let's talk about the layout. So commercial FPGAs implement island-style architectures. So island-style architectures are essentially a 2D array of logical blocks. There's different types of this though. So we have a neighbor, nearest neighbor style, which is essentially the blocks connected to its nearest neighbor. Very short-term communication. Assume I want to send a message to a block 100 blocks away. I have to go through other logical blocks, and a lot of switching is involved. The next is segmented routing. So segmented routing is basically switch boxes along communication highways, and each logic block is connected to a vertical and a horizontal switch box. So let's say this block wants to communicate with this block. So the switching can be done externally to route my signal from here to here. So there's still a lot of switching and there's still a decent amount of delay between them. However, this is an advantage over nearest neighbor because the other logic blocks aren't consumed. Like this logic block is not involved and this logic block is not involved, so they can be used for other things rather than just propagating a signal. A final implementation is hierarchical. So hierarchical is basically when you have these clusters of logical blocks, and at the edges of the blocks are these longer wires, these clusters. So there's fewer longer wires, but the longer wires that do exist don't require switching, and there's less delay in communication. Let's talk a little bit about parallelism. This is some more abstract stuff, such as stuff that would be implemented in a regular CPU, like there's two ways, message passing and shared memory, which are ways to implement parallel processing, ways for processors to communicate together. What I really want to focus on, though, is how FPGAs need to be treated differently in a parallel environment. So one of the things that makes optimizing FPGAs so hard is Amdahl's law. This says that in order to achieve substantial speed up, almost every area of the application has to be improved. This makes sense because if you have a bottleneck and you're not able to optimize that, that's always going to limit your performance. You're not really going to be able to get any benefit from improving other areas. So I read an interesting paper that offers 12 ways to really improve this, but the main thing I want to focus on is systolic arrays. So systolic arrays can take many forms. They're used for processing and a lot of intense communication between elements of the arrays. So these arrays are similar to an n-dimensional pipeline. Some of the major advantages in applications are for matrix applications, data structure manipulations, image processing, etc. So using systolic arrays provides an advantage over priority queues, stacks, trees, etc. So another thing I want to point out is latency hiding. So latency hiding is another way to improve your performance. It simply lays out functions on the same chip to operate in parallel, but when one function has to wait for a high latency operation, you switch tasks. This is exactly what CPUs do, CPU scheduling. I've taken a class where I've learned about CPU scheduling algorithms, and I can assure you this is exactly the same thing that they do. This is the essence of parallel processing, keeping the CPU or the processor as busy as possible. The same goes for FPGAs. So in short, you can read this whole section, but achieving a high level of processor utilization is not easy. However, it is doable with enough background and hard work. So there's benefits of FPGAs that go far beyond its processing speed. However, there are disadvantages, and one distinct one I want to point out is the power consumption. So application-specific circuits, integrated circuits, are designed. They're designed to be the best at what they do. They're designed to be the fastest at what they do and the most optimized in terms of power usage. FPGAs are more flexible, but they do consume more power. So at the transistor level, there's two types of losses: dynamic and static power consumption. Static power is leakage power, basically, from leakage of transistors, even when they're off. Dynamic power is power due to switching. So we know that switching losses occur due to internal capacitance of transistors. As you can see, when compared to microprocessor, the FPGAs always lose in terms of power consumption, especially static, as you can see here and here. So what can we do to minimize the power consumption of FPGAs? It looks like quite a problem. Well, there's something called pipelining. Pipelining is very useful because it allows you to save power and speed up your applications. So consider this scenario. You have a large multiplier, a 16-bit array multiplier. And this multiplier has many, many full adders. Each of these little blocks is a full adder. Now in FPGA, there's a phenomenon called glitching, which is when you trigger one, when a signal changes in one of these units, it will trigger all connected to it. So you can see that if you had a glitch in one of these adders, you can trigger 79 additional adders, which is a lot of lost power. Now pipelining is basically just putting flip-flops across sections. You can minimize glitching and speed up. So here you can see that on this flip-flop, it's not going to allow a signal to propagate until the rising edge is reached. So now you trigger far fewer and save a lot of power. There's applications that go beyond just big computational data centers. There are innovations taking place in the embedded world. You may see FPGA processors in the embedded world. You also see intellectual property cores. Something that I envision someday is maybe Intel or a company that designs these processors may be able to create VHDL for the processors and then send these out to their customers so people can get CPU updates and just synthesize their own CPUs rather than purchasing a new fabricated one. So this could be interesting. And then lastly, in industry as well. So conventionally, PLCs are used to do a lot of industrial control, but if you come up with more complicated control algorithms like model predictive control, the computation gets expensive. So FPGAs might be able to provide better use. So I would like to thank Dr. Praveen Maduri for providing me with the necessary resources to complete this paper, and I would like to thank the UB Libraries for providing me with the material itself. Thank you for watching, and have a nice day.